Hey everybody, it's Mr. Francis, and this is a review for Chapter 19. We're going to get into electrochemistry, and we'll get a little history, but there's actually two areas that we're going to focus on. One is the reactions that you see in an electrochemical cell, and then the calculations for that, along with the construction. So again, a little bit of history, whether it's a battery or a battery cell, the construction of it always seems the same. There's always two metals, and there's always a separation between the metals themselves. Um, Batteries don't have to be that, fancy. You've probably done this experiment in a high school or middle school class, taking a lemon and using that to produce a voltage with it. But again, you've got two disparate metals here with that. Okay, a lot of our focus is going to be on voltaic cells, and you look at the aspect here, and what's important about a voltaic cell is this aspect. It's a spontaneous reaction in the cell itself. The first part of chapter 19, we're going to focus on the balancing the half reactions that we see in the electrochemical cell, the voltaic cell, and the movement of the electrons. What we're going to see with this is, like I said, with the balancing for that. In an electrochemical reaction, it's also known, again, we go back to that oxidation reduction reaction. So we are going to bring back oxidation numbers. So again, a couple things just to remind you, being oxidized and reduced. Oxidation, remember, is when the substance loses electrons. Reduction is when the substance gains electrons. In terms of oxidation numbers, if a substance undergoes oxidation, its oxidation number increases, and a reduction, the oxidation number decreases. We're going to focus on those reactions that occur in an acidic solution, and you'll see why here in a minute. Okay, so here is this first reaction, and what they've done for the iron and the manganese is they have assigned the oxidation numbers for each one. So you can see for the iron here, it's gone from 2 to 3. For the manganese, it's gone from +7 to +2. These oxidation numbers, you can go back to chapter 4, which has the rules for oxidation numbers, assigning the oxidation numbers with that. Okay, so we are going to balance these. We start with the oxidation numbers, but we're going to take this reaction and any other reactions and split them up into half reactions. So what we would do with this particular reaction, we'd take the iron, and that would be a separate reaction, and then the manganese would be in a separate reaction. Okay, here's the steps. Everything starts by balancing all the atoms except for these two, the hydrogen and the oxygen. Once you have all the atoms balanced, and this typically is the one mistake that students make, they all forget about balancing all the atoms. Then we balance the oxygens, and you can see the step. We add water to the side that needs the oxygens. We do the same thing with the hydrogens, but now we add the hydrogen ion. And then this last step. In the half reactions, not only do all the atoms have to be balanced, but the overall charge has to be balanced. So we add electrons. And in this step, pay attention to coefficients that you have in there, because that, that varies with the charge. And then the combination. And in the combination, we want those electrons to cancel out. And you're going to see that in the examples for this. Okay, so again, we go back to the iron and the permanganate reaction. We start with this. Hey, we got iron, just iron. Hey, they're already balanced. And again, now we're going to add the electrons. And remember what they said with this. You add the electrons to the more positive side. So in this case, hey, we're adding one electron because we're +2 here, we're +3 here, so we add the electron. Here's the manganese. Okay, so again, we balance the atoms first. So we're going to balance the manganese. They're already balanced. Now we balance the oxygens. MnO4, okay, so we've got 4 oxygens here. We're going to add 4 waters. Now we balance the hydrogens. Hey, we've got 8 hydrogens, so we put 8 hydrogens over here. So now we're balanced overall. Now we've got to balance the electrons. Think about our overall charge here. On my product side, water has no charge. Manganese is +2. On the reactant side, the permanganate, the MnO4, has a -1 charge. The hydrogen's +1, but there's 8 of them. So that's 8 plus 8 total. So this side you actually have +7 and +2. So that's where you're seeing the 5 electrons. Again, pay attention to that coefficient. Now we want the electrons to cancel out. Again, 1/2 reaction had a single electron. We had 5 over here. So we're multiplying this reaction times 5. Now the electrons cancel out. And what we're left with is our balanced reaction. The key to balancing these oxidation reduction reactions, these half reactions, again, step at a time, but follow the steps. The steps don't change with this. Again, here's the second example, and we'll kind of go through this a little bit. Here's our overall reaction that we want balanced. Watch how they split the half reactions. So it's the zinc, and then the nitrate and the ammonium ion. And as you go through each of the steps, hey, this is balanced here. And again, you're going to know if it's a charge because there will be a charge up here. This is 0 plus 2, so we add the 2 electrons. The nitrate, here's this reaction. And again, go through the steps. Balance the nitrogens. We've got 3 oxygens, so we add 3 waters. That gives us 6 hydrogens here, plus 4. So that gives us 10. And again, we add the electrons to the more positive side. We've got plus 1 over here, plus 10, minus 1. Hey, that's plus 9. So plus 9, plus 1, there's where you get the 8 electrons. We want the electrons to cancel out, 2 and 8. So hey, we're multiplying that by 4. The electrons cancel out. We get our overall reaction. Okay, so there's not a whole lot of difference. Just kind of go through it step by step as you do this. Okay, electrochemical cells is the major term. They can be one of 2 types. A voltaic cell, which again is a spontaneous reaction, or an electrolytic cell, and the difference here is a non-spontaneous. We're going to focus on voltaic cells. The construction, actually pretty simple. Everything is in 2 half cells. One's the oxidation, one's the reduction. And you can see here, this is a zinc and copper half cell. So here's our zinc, here's our copper. We've got a salt bridge, which, if we go back here, that keeps the solutions apart. And we've got 2 terms that are very important, anode and cathode. Every cell has an anode and a cathode. And this is also important, the flow of the electrons. They move from the anode to the cathode. And here is essentially a schematic of a very simple voltaic cell. Our anode over here is the zinc. The anode is where oxidation occurs. The cathode is where reduction occurs. We can use a voltmeter to show the movement of the electrons. So that 1.1, that's the voltage, that's the movement of the electrons in the system. And again, this is just an example that we put through with this. Okay, there is a shorthand notation for voltaic cells, and what's really easy, this notation down here, your anode is always on the left, your cathode is always on the right, and then you got the double lines there in between. So again, anode, that's our oxidation, cathode, that's our reduction. And again, essentially they're written out as the oxidation, as the reduction reactions themselves. Hydrogen can be used as as an electrode, but one of the things you'll always see with hydrogen is platinum. Platinum's a great metal to catalyze the hydrogen. And again, you can go through these examples and note how they take the notation and write out the cell reaction for each one. I'm not going to go through overall with it. Again, electrons are always moving. They move from the anode to the cathode. It's like water. Water moves from high pressure to low pressure. Electrons do the same thing. We can calculate that difference, and that's that voltage that you see on the meter. The SI units, the volts, is a combination of joules and coulombs. And we have this if we're calculating work. Work is equal to Faraday's constant times that potential difference. Again, note the sign, it's negative. Work is being done by the system. That potential difference is what we call the E cell. And that's the second part of the chapter here, is how we can calculate and determine the E cell for a system. We can calculate work, and you look at this. Maximum work is equal to a negative NF E sub cell. F is Faraday's constant. N, that's the number of electrons in the overall system. And E cell is our potential difference. And here you got this example in terms of your calculations. And you can see how they're putting together. They actually give us our value for N. They give us Faraday's constant. They give us our voltage. There is our work. And again, voltage, coulombs, that's equivalent to a joule. And then they do the work for calculating for grams. Okay, we want to calculate this E cell. And this is the reaction, as we'll break it down, that we want to take. It's the oxidation potential plus the reduction potential. Except in chapter 19, or in table 19.1, you've got a complete list of reduction potentials. Well, here's the thing. If these are all reduction potentials, the reverse of them would be the oxidation potentials, and the sign would change for each one of them. So, if we're wanting to calculate this E cell, again, here's my anode, here's my cathode. So I go back to table 19.1. Here is the copper one as a reaction, so the 0.34 volts. The aluminum is oxidized. But again, if you go to this table, here's aluminum. Its reduction potential, negative 1.66. So its oxidation potential would be the reverse of that, 1.66. And that's what they show here. And then you just add the two together. And that's going to be important. E cell is going to be your anode plus the cathode. Table 19.1 is going to be a great reference table for you. Continue to use it knowing, hey, my oxidation potential is just the change in sign from the reduction potential. Again, most of these are measured at a standard state, 1 atmosphere, 1 mole, 1 molar solution, 25 degrees Celsius. The strength of the agents, the stronger reducing agents are going to have the larger negative value. The stronger oxidizing agents have the more positive value. Again, something to remember there. And again, these couple of examples of arranging the substances with that. So again, if we're going to arrange these based on the first one they say is oxidizing agents. So the oxidizing agent is going to be the more positive. So in this case, the peroxide with the higher voltage, that's the stronger oxidizing agent. By increasing oxidizing strength, the iron here is the weaker of the oxidizing agents. And then the second one, again, now that these are again reduction potentials, they're looking for reducing agent. The copper, so the aluminum, because it has the lower value, is the stronger reducing agent. We talked about in thermochemistry the relationship between maximum work and delta G. So hey, this equation, delta G, can also equal this negative NF E cell. and we can calculate. So if we've got, here's that zinc silver reaction, we calculate the E cell, and we can calculate the delta G for this. And the same thing with the zinc and chlorine. We can calculate our delta G, and then from that delta G and finding the value of N, we can solve for E cell. And there is a relationship between delta G and the equilibrium constant. You've got this equation here, and really all you need to know is your E cell and your N. How many electrons do you have moving through the system? I like this figure. It relates delta G to a number of things that we've talked about in thermochemistry and now in electrochemistry. And again, you can calculate the value of K with this. And again, think about your equilibrium. The greater that value of K sub C, the more products get formed with that. And then you've got what they call the Nernst equation. Again, these are plug and chug equations that you can plug in. And the pH. The last part, and I'm not going to go through this, but they've got some commercial voltaic cells that you use on an everyday basis. What the battery in your cell phones look like, the rechargeable batteries, AA, AAA, what they're going to look at. Get a chance to look at those. So if you have any questions, feel free to contact me. But take care.